Alrighty guys, so we're going to go over a problem regarding weak acid strong base titration at equivalence point. I said it's going to be on your exam, so I wanted to give you guys a video that you guys can study off of. So in this problem, we are looking for the pH at the equivalence point where you're titrating 50 mils of a 0.1 molarity acetic acid solution with 0.1 molarity NaOH, and you have the Ka value. Alright, so before we start doing any calculations, let's just talk about what's going on. So you have your acid, and this is going to be a weak acid. You have your acetic acid. The volume is 50 milliliters. The molarity is 0.1. And you are titrating NaOH, which is a strong base, and the concentration is 0.1 molarity. Okay, so this is your strong base, and this is going to be your weak acid. Alright, and we are going towards equivalence point, which means that we're going to be titrating until the moles of base that have been added are equal to your moles of acid that are in the original solution. Alright, now what makes it a little bit different because it is a weak acid is that it's going to dissociate on its own even before you titrate the base in. So this is where the first ice table comes in. And we'll call this the pre-titration ice table. This is where the acid, the weak acid, before you add anything, is just dissociating on its own. So take a second to pause the video, see if you are able to write the dissociation equation for the weak acid on your own. So pause the video. Alright, so you should get something like this for your dissociation. If you switch the H and the anion, that's totally fine as well. And you got your ice table. Well, initially it tells us that we have 0.1 molarity of our weak acid, and then we're going to just look at how it dissociates by itself. So you're going to be losing some of your weak acid and gaining your conjugate base and your hydrogen. So this is how you will finish up the ice table. And I do want to let you guys know, if you are able, see if you can pause the video at different points where we are filling out the ice tables and doing the calculations, and see if you're able to complete them on your own. It's the better way to practice rather than just watching me solve the problem. So make sure you're following along and solving the problem. Pause the video when you need to, see if you're able to get it, and just check your answers with my video. Alright, so this is how you should complete the ice table. And before we fill in our values, we're going to have to use our Ka value. So our Ka is 1.8 times 10 to the negative 5. And we know that the equilibrium constant expression is products divided by the reactants. Okay, we can use the 5% rule, so we can pretty much ignore the change because it's going to be negligible. And we're going to multiply both sides by 0.1. So our math is going to be 1.8 times 10 to the negative 6, which is equal to x squared. So in order to find x, all we have to do is find the square root. So our value for x is going to be 0.0013. Okay, and that is going to allow us to plug in our values right here and find the molarity for each compound in this solution. So what this is going to tell us is that for the concentration of our weak acid is going to be 0.0987 molarity. Okay, we're going to get it like this. For our x values, for our conjugate base and for our hydrogen, we're going to have 0.0013 molarity for each of them, because that's just x. We're just plugging in x into our ice table. Now, before we start reacting, before we start doing the titration, we need to convert this into moles. And so we're going to take the new molarities that we have, and we're going to use the molarity formula with the volume of our acid in order to find our moles. Now, if you guys remember, molarity is equal to moles over liters. And so if you convert 50 milliliters into liters, you are going to get 0.05 liters. You're going to look for moles, and you're going to use each respective molarity in order to find the moles. So see if you can pause the video right here and solve. Okay, so you're just going to be multiplying your molarities by the 50 milliliters, and you should get these values for each compound. Alright, so what this is basically telling us is that this is how many moles of each respective compound you have in your acid solution before you start the titration. Okay, so these are the values that we got from the first ice table that are going to transfer over into the second ice table. Alright, so the second ice table is pretty much where you're going to do the actual titration. And so you're going to be adding your base into your acid solution. So we're going to first start by writing the neutralization reaction. So we're going to take our weak acid, and it's going to be reacting with our base. Now we know that NaOH is a strong base, so near complete ionization. So we can just substitute it as OH minus, and it's a 1-to-1 ratio between the base and the hydroxide. So we'll write OH. We're going to draw an arrow going forward because it's a strong base, so it's not going to have a reverse reaction. And what this is going to do is it's going to produce a conjugate base and water. And we know that water is a liquid, and so we can omit that from our ice table. We don't need to worry about pure substances when it comes to the ice table. All right, now the difference between this first ice table and the second one is instead of working with molarity, we're going to be working with moles because it'll just make our calculations a little bit easier since we're going towards equivalence point where it's going to be moles of base is equal to moles of acid. So let's take our values that we got from the previous ice table and see if you can pause the video and plug it into this ice table. All right, so these are the values that we're pretty much transferring over. We have our weak acid right here, moles, and we have our, excuse me, not that one. You have the moles of our anion. Now, we have to go to equivalence point, so we need a value for how much base we're adding. But if you guys remember, equivalence point means that the moles of base added is equal to the moles of acid that was in the solution to begin with. So if we start with 0.004935 moles, that means we are going to be titrating in 0.004935 moles of our base. All right, and then the acid and the base are going to neutralize one another, so we're going to be losing the same amount of each. Okay, so we're going to end up with zeros for our two reactants. And for our product, we're going to be gaining the exact same value. So you're going to end up with 0.005, and this is going to be moles of our conjugate base. So what's happening is you start with your acid, you titrate in base until it reaches equivalence point, so you end up with none, and you are left over with your conjugate base, okay, the anion. Now, before we move on, what we want to do is we want to find the molarity now that we have titrated in our base. However, if you guys recall, we started with 50 milliliters of acid and now we've added some base. That means we have added a certain amount of base into our acid. So that means our total volume is going to be different now. It's not going to be 50 milliliters. And so that's what we need to figure out. Very simple to do that. We're going to use the molarity formula again, but this time we're going to be looking at our base first. If you take a look, the base that we added is 0.1 molarity. Okay. We know that we've added 0.004935 moles of that base. And so what we're looking for now is we're going to be looking for the volume of base that we added. So see if you can pause the video and calculate how much base, the volume of base that you added. Okay, so this is what you guys should get, about 49 milliliters. All right, now that's going to be the liters of base added. So this is going to be our NaOH that we added. Okay, we started with 50 milliliters of acid. Okay, and so our new total volume is going to be about 99, about 0.1 liters. Okay, and so for our molarity of our conjugate base, we're going to take our 0.005 moles divided by the new volume, and that is going to give us our the molarity, the concentration of our conjugate base. All right, so what all these calculations are telling us is that once you titrated in your base into the acid, the only thing you have left over is this right here. This compound right here is going to be a conjugate base, right? It's the conjugate base of acetic acid right here. And because it's a base, this is actually going to affect pH. So this is going to affect pH. Okay, so this and water are the only things really left inside of your of this container after you titrate it. And so water obviously is neutral, but this base is going to affect the pH, and that's what we're going to be figuring out with our third ice table, the final one. All right, so we're going to go into our third one, and then we'll call this the post-titration ice table. And this is where we have our CH3 CO minus, our acetate. This is our conjugate base. Now, if you guys remember, what does a conjugate base do? A conjugate base is going to react with water, and it's going to go into equilibrium to form its acid and produce hydroxide. Okay, so we're going to set up an ice table for that, and at the end of this, we'll have the numbers that we need in order to calculate the pH. All right, so our starting concentration of acetate is 0.101 molarity. Okay, water is a pure substance, so we don't need to worry about that for the ice table. And we're going to put zeros for this. So what's happening is once you neutralize and get to equivalence point, you're going to have some acetate left over. And the acetate is going to start reacting with the water and start going into equilibrium. Okay, so from here, pretty basic ice table. You're going to lose this, gain this. Okay, and this should look pretty familiar. This is very similar to an ice table that we've been looking at since the previous unit. Now, this is going to allow us to solve for our K value, and it's going to be the same thing, products over reactants. And since we're using the 5% rule, we can ignore this right here. However, we cannot use this Ka value because this is going to be a base. A Ka value refers to when you are dissociating an acid. And so this expression right here is not for Ka, this is for Kb. So we cannot use this 1.8 value just as our K value. Instead, what we have to do is we need to find Kb using Ka. If you guys take a look at your AP equation sheet, you should see this relationship. Ka times Kb is going to equal the Kw. And Kw is going to equal 1 times 10 to the negative 14. And so what we're going to be doing to solve for Kb is we're going to do Kb is equal to 1 times 10 to the negative 14 divided by Ka, which is 1.8 times 10 to the negative 5. So see if you can pause the video and see if you guys can solve that on your own. Okay, so you guys should have gotten 5.55 times 10 to the negative 10. All right, so that is going to be our expression that will allow us to solve for x. So we can fill in our values into our ice table. Okay, so pretty simple calculation from there. You multiply both sides by the denominator, and then you find the square root. That's going to give you a value of x is equal to 7.5 times 10 to the negative 6. And what we can do with this value right here is we can plug it into the ice table to find our OH concentration. Okay, so that means that the concentration of OH after the titration is going to be 7.5 times 10 to the negative 6. Now, if we go all the way back to the beginning, what the question was originally asking us, it was asking us to find pH. If we have the concentration of OH, what we can find is POH. It's going to be the negative log of the OH concentration. Okay, so what we can do is we can plug in our concentration, and we'll get a POH of 5.1. Okay, and then lastly, to finish off, we know, and again, this is on your AP equation sheet, pH plus POH is equal to 14. And so in order to solve for pH, all we have to do is to do 14 minus the POH. So our pH is going to be equal to 8.9. Okay, and a great way to check your answer is just think about this logically. At the end of the titration, what do we have left over? We have a base. The base is going to make the solution basic, which means that the pH should be greater than 7. And if you look at your final answer, our pH indeed is greater than 7, which means that our answer is reasonable. Alrighty guys, so that is how to find pH at equivalence point with a weak acid strong base titration. Again, this is guaranteed to be on your exam, so just make sure that you're able to do a problem like this on your own. I believe that this problem is on the class workbook, so make sure you guys can do this on your own. A good way to practice, try the other one, 68, and that should help you guys out. Again, just a reminder, the best way to prep for our exams is to do as many practice problems as possible. I pretty much laid out how to solve this problem, so I would recommend going through it, see if you guys can solve it on your own. If you ever get stuck, you can always refer back to the video to kind of see the next step in the process. But again, this is going to be on your exam, guaranteed. So make sure that you are able to solve this problem on your own. All right, good luck with your studying, everybody.